Haha, and I'm live. Excellent. All right. My ultimate goal for today is to continue working on what we've been doing with random variables. I have an open-ended type problem for you guys to work on that I'm going to pass out in a little bit. For those of you that are in the live stream, I'm going to be posting the PDF to the Google Classroom in a few minutes. Well, maybe not a few minutes. Maybe I'll actually do something else first. Yeah, I probably got to wrap up something in regards to the notes from last time, so we'll probably do that first. But yeah, then I want to continue working through this worksheet on random variables, kind of see where that goes. You do have an assignment out of the textbook for me based on some of the previous probability stuff that we've been doing. I would like that done, obviously. It's due today, I believe, at 2 o'clock. I set it for. I will be making a video reviewing said problems in order to save a little bit of time in class, just because I want to make sure that you at least have the review to those problems. But yeah, we'll get there when we get there. In the meantime, for a very brief amount of time, because I just have to finish up some of the statements I made last time, I'm going to need those notebooks out and open. Okay. Last class, I left off on the following kind of statement. So let me point out where all of this came from and then kind of reiterate one of the major points I want to make here. Within the confines of random variables, there are going to be certain instances in which you have to combine standard deviations. And if you have to combine standard deviations, you cannot just add them together or subtract them for whatever the thing is asking for. Instead, you have to convert standard deviations to something called variance. Simply put, variance is equal to standard deviation squared. So, well, if you have a standard deviation and then you square it, you convert it to variance. Then you can perform the operations that the problem is asking you to do. Kind of. If they ask for the random variables to be combined through addition or something along those lines, summations, yes, convert the standard deviation to variance, add the variances together, and then boom, we have it, and you can convert it back, which I'll talk about in a little bit. But if you're looking for the difference in standard deviations, you follow that same procedure, you convert to variance, but you are still adding the variances together. And I purposefully wrote this line here so that you know, and I want you to write that. If you did not write that last time, write it this time. This is not a typo. There's a reason for that. Now, we ran out of time last time. Some people were kind of giving their ideas as to why that was, but I wanted to try and give an example, kind of a visual example as to why that is what it is. Think about what standard deviation actually is. Standard deviation, for the lack of a better term, is the average deviation from the mean. Standard deviation measures how spread out your data is. Standard deviation is a measure of either the consistency of the data, meaning it's pretty close together, or the wide variations in the data, meaning they're a bit more spread out. So if you have, there it is. If you have a standard deviation, let's say standard deviation of X, by the way, this part you don't write down. I just wanted to kind of show this. Let's just say the standard deviation of X is like 2. Okay. That means that on average, the data deviates by 2, meaning it could deviate either in 2 in the positive direction, or it could deviate by 2 in the negative direction. Standard deviation is always going to be a positive number. It's always going to be a positive number. It could just deviate either in the positive or the negative direction. But then I have the standard deviation of y. Let's just say it was 3, for example. And again, same concept. It's a different random variable. It's a different set of data. But that standard deviation is deviating by 3, meaning either 3 in the positive or 3 in the negative direction on average. Obviously, data points are strewn throughout. Now, if I were to combine these two standard deviations, whether it be through addition or subtraction, the thing to think about is that this data, as I said, could be anywhere from -2 to +2 away from the mean. This data could be -3 to +3 away from the mean. Now, obviously, if I were adding them, that makes a bit more sense. It'd be like, okay, I'd convert it to variance, I'd add them, square root them back, and that would be the combined standard deviations. But if you're talking about the difference between them, the y data here could deviate as far as 3 in this direction. And the x data could deviate as far as -2 in this direction. Now, obviously, this is not what you would do. You would have to convert them to variance. But think about a data point that's deviating a bit far this way versus a data point that's deviating a bit far this way. What happens when you try to do something like 3 minus -2? What ends up happening? Yeah, you end up adding them. It's kind of a weird situation. The distance between them ends up being a bit larger. Hey! Yes! Whatever. Anyway. That's 1 for the year. I got the door on you. Ask your brother how many times I got him. Yeah. Anyway, that was fun. Hey, where was I? Lost my train of thought. Yes. When you end up subtracting a negative and ends up being plus, like you talked about, it ends up being a larger distance. So it doesn't matter whether you are combining the deviations through adding or subtracting, the deviations end up being a bit larger. They end up being a bit more varied. Another way of kind of explaining it is the idea that, like we said, actually, no, I shouldn't have erased those. Whatever, I'll put them back. Another idea would be something like this. I'll put these same numbers up here. If you have to convert them to variance, let's say I wanted to do the variance of x minus y, and I wanted to subtract them. So I would square this to get 4. I would square this to get 9. But then if I had to continue with subtraction, I would get a negative number. And if I tried to square root that back to standard deviation, all of a sudden the whole thing falls apart. So not a typo. I got to add them. Just one of those weird quirks in statistics. Total side note, total side note, kind of unrelated to this. I just wanted to ask because it was on my mind. Does anybody here, like, either now or back in the day, play like a lot of Minecraft?
Yes.
Okay. Are you familiar with the controversy behind the speedrunner of Minecraft, a guy named Dream?
Yes.
Okay. I just watched a video on it today. The statistical analysis that they did against this guy is spot on. I just want to point that out. And we're actually going to not get into those details, but we're going to get into similar type statistical analyses probably in like February, March. So I watched the video this morning and I was just so excited. I'm just like, yes. I don't know. What? I know, right? It's just like, what the heck? No, the general idea of what they did was they tried to figure out, okay, assume for a moment that like there is like a certain truth behind it, like a certain spawn rate of items, like 4%. Assume that that's correct. If that's correct, what are the chances that he would get something like this? And it's literally what we're going to be doing. But anyway, I digress. Back to this. Oh, I got too excited for a minute. I had no idea you guys were that into Minecraft. Oh, I'm sorry.
Did you see his response video to it?
I didn't. I heard about it. I heard that he hired somebody.
A professional statistician, like a PhD.
Whatever.
And he did like a really in-depth one.
Okay, that's fine. You know that he can totally do that. But I'm just saying, like, no, I can't. No, I will talk about that probably a bit more in like February, March. You know, but we'll get back to this. So, not a typo. Make sure you write that down. Now, a couple of things to add to that. A couple of just statements that I didn't have time to write down last time. You can't combine or alter standard deviation, but you can do it with variance. You can't combine or alter standard deviation, but you can do it with variance. Why is this thing off? There we go. And basically, as I verbalized, convert standard deviation to variance. Like I said, the way we do that is, well, you square standard deviation. And if you square standard deviation, you get variance. Then you perform the operation, whatever that operation ends up being. In this case, obviously addition here. But you're going to see that with other things as well, because we're going to be doing some multiplying a bit later on. And then you convert back variance to standard deviation. That's mainly what we're going to be focusing on. Okay. Let me get these to you guys. I'm passing out a piece, for those in the chat, I'm passing out a piece of paper right now. I'm going to post that PDF of the paper in the Google Stream in a few minutes. 1, 2, I hope that was enough. See, the general idea, I will say this, though, about what I was talking about before. The general idea of statistics is that you cannot make definitive statements. You can do your analysis, but you can't make definitive statements or conclusions about things. Statistics is about putting certain numbers on trial. And when you put something on trial in a court of law, what are the only two outcomes? Yeah, you never proclaim someone innocent. You either proclaim guilty, meaning you had enough evidence to prove, well, not to prove, but you had enough evidence to show guilt, or not guilty, meaning you did not have enough evidence to show guilt, but you never proclaim innocence. That's what ends up happening in statistics. When it comes to hypotheses that we run, we either reject or fail to reject. So what I'm posting right now, I'm posting the PDF for today. Bam! There it is. There's the PDF for today that I just posted into the Google Stream. I wanted to talk about this particular problem in regards to what we've been doing. So for those of you in the live stream, you have the PDF of these problems. Yeah, happy day. Woo! As a side note, you will have to calculate a standard deviation in a few moments. Obviously, we're not going to be doing those by hand. So you will need the graphing calculator capabilities in order to get that done. Just giving you the heads up before we get there. For number 2, you have to calculate a standard deviation. And we use the graphing calculator to get that thing done for us. So this problem. A fast food chain restaurant, or a fast food restaurant, just released a new freezer and food fryer for 3 years. All right. Service contract for the freezer offers unlimited repairs for a fee of $125 a year plus a $35 service charge for each repair needed. The restaurant's research suggested that during a given year, 80% of these freezers need no repairs, 11% needed to be serviced once, 5% twice, 4% 3 times, and none required more than 3 repairs. That's a lot of information. We're going to have to organize that information in a few moments. Let me just kind of read this first question to kind of see what direction they want me going in. Number 1, find the expected number of repairs this kind of freezer is expected to need each year. Okay, expected number of repairs. This is what we were doing. We were working on some kind of gambling game in a previous class period where it's either going to be win-win, win-lose, all that other stuff. And we had to figure out the expected profit. That word expected carries a lot of weight. Expected value. What we would expect to happen given the certain conditions that they are throwing out at us. So let me flip some of this stuff around. I'm actually going to go to my physical paper right here so I can actually write on it. There we go. Zooming in, zooming in, zooming in, zooming in. There we go. Zooming out. Zooming out. Focus. There we go. Good, 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 good. Okay. Come on, paper. Move out of my way. Excellent. So I'm looking at this thing, and I realize that I'm going to have to create some kind of a table similar to what we did in regards to that gambling game. Now, in this case, we're not talking about profit. We're talking about number of repairs. So in this case, this X is going to be the number of repairs that I'm putting onto this thing. So it could need no repairs, 1 repair, 2 repairs, and none. Okay, and 3 repairs. Yeah, that's it. Because nothing's going to need 4 repairs. They make that little statement right there. None required more than 3. Now, logically, yes. I mean, you would expect, oh yeah, it could have more than 3. Yeah, I know. But for the purposes of our problem, they're sticking with 3 repairs as the maximum. All right. The probability of said event happening. Well, it says an 80% chance. Now I'm just going to convert it to decimal. 11% here, 5% here, and 4% here. Does that add up to 100? Cool. Then what they did is pretty solid. Okay, cool. Now, I know that the problem did state that the lease was for 3 years. But I'm going to ignore that for the simple reason that the question is asking for the expected number of repairs each year, meaning just in one single year, not for the 3 years combined. So with this, I mean, yes, we could easily go to the calculator and get this thing done, but I want to do this one by hand just for funsies. I'm going to multiply these together. Clearly, that's a 0. Clearly, that's a 0.11. Oh, that's a 0.10. And that's a 0.12. If I multiply all of those together, I can't see that. Let me zoom in. There we go. And then what do I do with those 4 numbers? Sure. 0.33. Yeah. 0.33 repairs. I can't see what I wrote. Zooming out. There we go. And of course, I'm going to show you that on the calculator in a moment because we're going to have to do the standard deviation. But if they just had you doing expected value, this is the proper process that you would go through. You have X, which is the numeric value of said event. You have P of X, which is the probability of that event happening. And then they say, okay, well, how many repairs could we expect to happen? This is the procedure that we would go through, where we would multiply together the numeric value of the event times the probability of the event, and then add up all of those individual numbers. Now, obviously, 0.33 is not a whole number. You can't do a third of a repair, but the idea is that on average, if you had many different independent situations of people owning that type of freezer, if you average together the number of repairs they have per year, 0.33. Or it should be, according to these percentages. Obviously, that doesn't account for conditions and how people treat their freezers and junk like that. Dead bodies and things of that nature. Anyway, I go back to my calculator. Where's my calculator at? Do that. Do that. Come on, you. Load SmartView CE. There we go. Clear that. Cool. In order to calculate the standard deviation, as I said, you would need a graphing calculator to get this done. We figured out last time how to actually do this properly. You will need to enter in your data into your list, stat edit. I'm going to type in a 0, a 1, a 2, a 3. I'm going to type in a 0.80, a 0.11, a 0.05, and a 0.04. Yes, even though 0 repairs does result in a 0 in the summation for expected value, you still need to type that in. You still need to have that there, especially for standard deviation, because it does give you a value that attributes itself to the standard deviation. Remember, standard deviation being, on average, how data points tend to deviate. Let's see, stat, calc, 1var stat, and as we discovered last time, under frequency list, you need to type in L2. Now, where you get L2, easiest way, second 2 will just get you that L2 right there. That makes sense because the first list is the number of repairs, and the second list is the frequency in which those repairs show up. 80% of the time, 11% of the time, etc. But you do need to do that in order to get the proper expected value, which, as you can see at the top, is 0.33. Which is nice. And then, of course, they do give you that standard deviation. I'm going to write that down. The standard deviation of the number of repairs would be approximately 0.75. I'm going to round it. 0.75 repairs. If you notice, they don't even give you an S there. They just give you the sigma. And I'm not even going to worry about a 5-number summary. That's meaningless at this point for 2 sets of data here. But that is the expected standard deviation, and that is the expected value. You can even see it's the sum. Yeah. Okay. Let's see what the next question has in store for us. Oh, make that a little larger. Click. Number 3. What are the mean and standard deviation of the restaurant's annual expense for the service contract? How long is the service contract? Yeah. Ooh, interesting. So the service contract is indeed 3 years. Oh, wait a minute. $125 a year plus a $35 service charge. Okay. Well, they did say annual. So I'm going to assume that 3 years is not going to come into play just yet. It's not going to come into play just yet because they want to know the annual expense. Okay. As I've said on a number of occasions, a lot of stuff in AP Stat is going to come down to proper interpretation of the problem. If we make too many assumptions, we are going to mess ourselves up. We really, really will. We have to read carefully and don't try to do too much. They just want an annual expense. All right. Oh, okay. So I could probably do something like this. Let's see. 0.33 times 35 plus 125. Oh, you can't see it. It's frozen. There it is. Interesting. Interesting. 0.33 being the number of repairs, $35 per service charge, meaning per repair, obviously. Let's see what happens here. 0.33 times 35 plus 125. 136.55. Now we run into a little bit of an issue. Now that's correct, by the way. That's correct. But we run into a little bit of an issue. Here's what I need you to do. I need you to go on a little bit of a fact-finding mission through your notes. I need you to go on a little bit of a fact-finding mission through your notes. I need you to go back to, I believe it was chapter 5. I want to say it was chapter 5. Chapter 5, we covered before linear regression. Chapter 5, I'm not sure if it was early December or late November or some junk like that. I need you to look up in your notes what affected standard deviation, or what type of operations affected standard deviation. When you find it, someone share what you found, and I'll tell you if that's what we need. Find it? What'd you find? What do you mean? Okay, so for standard deviation, in the original set of data, if you multiplied or divided, that would affect the standard deviation. What did I say about addition, subtraction? It doesn't. Now this is key. This piece of information is absolutely key. Let me repeat what we discovered in chapter 5. Now I'm going to make a little kind of a normal curve, what we did back in chapter 5. What I did was pretend this was a normal curve. Oh, you can't. I'm trying to put it on the live stream as well. Pretend this is a normal curve. If I took every single data point and I added 5 to it, it would just shift over like this, thus changing the mean, but not changing the standard deviation. Standard deviation would just be the same, because standard deviation is an average of spread, or a measure of spread. It shows how spread out your data is, how varied your data is, how consistent your data is. Now, this is an important piece of information, because right here, they asked, what are the mean and standard deviation of the annual expense? Well, 0.33 repairs per year equate to $136.55. However, we cannot do this exact calculation to figure out the restaurant's standard deviation of expense. We can't, because addition, subtraction does not affect standard deviation if you're doing that to every data point. So the conclusion that I'm coming to is this. This number right here, I'll just make a little note right here. This one was the mean expense. But then notice what I'm calculating right here. This is the standard deviation expense. Obviously, I'm rounding. Standard deviation is affected by multiplication division, not addition subtraction, if you're doing it to every data point. In this instance, yes, I'm going to multiply the standard deviation of repairs by 35, but that's it. I am not going to add the 125 because that doesn't affect the standard deviation here. Woo! It's a weird kind of roundabout thing that we did back in the day, but we do need to recognize that fact. How many times should the restaurant expect to have this freezer repaired over the 3-year term on the lease? You could pretty much like just, not, I don't want to say guess. Guessing is probably not the right word. But you could easily just figure out number 4 in your head. Just by kind of like thinking real hard about it. And then we got the answer number 4 right off the bat, kind of an intuition type thing. Over the course of the 3-year term of the lease, how many repairs would we expect to happen? Yeah? 2? Why? Why? Yeah, or 0.99. Yeah, I'm going to write 0.99. But you're right, logically. And that is correct. That's exactly what you do. All right. Now, there's certain terminology, like not terminology, notation that they do that I'm going to write down. Like there's the first year, the second year, the third year, and it's like, oh, it's just like 0.33 plus 0.33 plus 0.33. Yeah, it is. That's all you would have to worry about. 0.99 repairs. Or yes, logically, you just say 1. But I'm just kind of trying to be accurate on that one. It seems like a very straightforward question, but that's exactly all you have to do for that one. Now, we come to number 5. After we do number 5, I am going to give you an opportunity to try and do number 6 and 7 on your own. I'm going to give you a little block of time to get that done. But first, let's do number 5. Number 5, what is the standard deviation of the number of repairs over the 3-year term on the lease? On what assumption does your calculation rest? Do you think this assumption is reasonable? We'll talk about those other 2 questions in a moment. But the first question, well, I cannot just add the standard deviation together 3 times. I can't. Instead, I have to convert it to variance, then add them together, then convert them back. So let's see, 0.75 squared, 0.5625. Well, adding it together 3 times is like, I just multiply by 3, really. Cool. I'm going to write this down, of course, and then I square root it back. Cool. That's all that you really have to worry about for this problem. So let me write some of this stuff down. Ba-bam. I would have to convert it to variance, which is 0.5625. I would have to add it together 3 times. Get you 1.6875. Lassie. I thought they come in 3s. Okay, never mind. Yeah. That's just weird. Anyway. Goodness gracious. Yeah, this is the repairs. Now, I probably should have put that as like 1.3, but I'm going to leave it as 1.299 for the sake of argument. Yes?
Why did we convert this one to variance and not number 3?
Good question. The reason, or not the reason, but the whole premise behind converting to variance is when you are trying to combine 2 distinct standard deviations. Whereas in number 3, thank you. And number 3, you weren't trying to combine two distinct standard deviations. You were trying to just convert a single standard deviation by a multiple. The idea of random variables or combining random variables, that's when it comes down to, yes, I have to convert to variance, you know. Now, 2 amazing questions here. On what the first one, on what assumption? On what assumption does your calculation rest? There is an overbearing assumption that you need to recognize in regards to this problem number 5. It has to happen in order for this calculation to take place. And if this assumption is not met, then this calculation is invalid. What might that assumption be? Ooh. Now, while you're thinking about that, let me clarify one thing. These are technically the exact same number, but they're 2 distinct standard deviations, meaning that this is the variance, I should say. This is the variance for year 1, the variance for year 2, the variance for year 3. That's how I'm justifying them being distinct from one another. But I go back to the assumption problem. Ooh, on what assumption does your calculation rest? When it came down to probability or multiplying probability, I gave you 2 different formulas. A couple chapters ago, I gave you 2 formulas on multiplying probability. What was the distinguishing factor between those 2 formulas? Ooh. It has to do with this assumption. Where are you, marker? So, like, for example, I would say, hey, guys, the probability of A and B is equal to the probability of A times the probability of B. Unless there's this certain assumption that takes place, and then if that's the case, then this formula changes. Yeah? Whether it's dependent or independent. Yeah. On what assumption does your calculation rest? It rests on whether or not the number of repairs from year to year are independent of each other. Each year is independent from the next. That is the assumption that has to take place in order for this calculation to be valid. The number of repairs from year to year are independent from each other. That assumption has to happen for this calculation to take place. But then they ask a follow-up. Do you think that this assumption is reasonable? Ooh. Now I ask you, think about real life. Real life. You own a freezer. On average, you expect 0.33 repairs per year with a standard deviation of 0.75. Are you assuming that each year of owning that freezer is independent from the next? Why? Have you ever owned a home? That's the key. I'm going to repeat what you said for the people online. But basically, if you have a repair one year, it's more likely then that you would need an additional repair in the subsequent years. That's absolutely true. That is absolutely true. Do you think this assumption is reasonable? Do you think each year is independent from the next? No, unfortunately, no. It depends on so many different things. But more importantly, just to kind of bare bones it, it depends on whether or not any previous repairs have been made. The number of repairs or the standard deviation of repairs needed in year 3 is going to depend upon what happened in the years prior. Because if you have, and if you ever had older siblings who have had car troubles, once one car trouble happens, all of a sudden the next year it's like multiple car troubles happens. Yeah, it keeps compounding on itself. That was a long verbal way of saying it. The way that this thing says it is, the assumption is that the number of repairs is independent from year to year. Yes. This might be incorrect because some freezers might need more service than others. It depends. It also depends on what you're storing in it. Don't store them bodies. Anyway, I want to give you the next little block of time. I want you to knock out number 6 and 7. Do your best with what you believe number 6 and 7 should be. We'll reconvene in like, I don't know, 5 or so minutes. I'm going to give myself a little wiggle room there. let's see where this takes us. Because I have these two problems, and I have one more that I have queued up on the computer that I want to show you in a minute. Let's talk about this one. The yearly service contract for the food fryer estimates a mean annual cost of $140 with the standard deviation of 40. That information is on the food fryer. We haven't talked about the food fryer at all since the beginning of the problem. At the beginning of the problem, it said that the fast food restaurant just leased a freezer and a food fryer. And then it just talked about the freezer and nothing but the freezer the rest of the way. And now all of a sudden down here in number 6, they reintroduced the food fryer. And they're like, okay, well, the food fryer has a mean of $140, standard deviation of 40. What's the expected value and standard deviation of the cost of the service contracts now for both pieces of equipment? Well, simply put, they're both F, so I don't really want to abbreviate. I could do free and fry, but I could do like my pen's not working. The expected value of the freezer plus the fryer is just simply put, well, I found $136.55 plus $140 should give me $276.55. And yeah, it should. Absolutely. Because with expected value, I could just add those things together. Oh, happy day. But now with standard deviation, I can't. I have to find the expected total sum of these two pieces of equipment added together. I'm going to have to convert things to standard or to variance, then combine them, then convert them back. So this would really be, what did I put? 2625, 2625 squared to convert to variance, plus $40 squared to convert to variance. Add those two things together to do 2625 squared plus 40 squared. Gives me some large number, 2289.06, but 2289.06, but that's variance. I have to convert it back. To convert it back, I get approximately $47.84. That would be the expected combined standard deviation of the freezer and the fryer together in their service projects or contracts. But now number 7, which service contract should the restaurant expect to cost more each year? How much more? Well, clearly the food fryer is going to cost more. That's a given. But how much more? Well, that's a problem where I would have to subtract the two of them. 140 minus 136.55 gives me $3.45. On average, it would cost about $3.45 more on the service contract for the fryer. What about the standard deviation? Well, I'm not going to bother changing anything, because if I'm going to find the difference between the two standard deviations, not a typo, the standard deviation would still be $47.84. Because I would have to do the exact same calculation, where I would have to square each standard deviation to variance, combine them, square root them back. Yeah. Done and done and done and done. It's a weird thing. One last problem that I want to throw at you is right here. Let's zoom in a little more. Zoom out a little bit. There we go. Okay. I'm going to read this one for those in the chat if they can't see it. On a physical fitness test, middle school boys are awarded 1 point for each push-up they can do and a point for each sit-up. The national results showed that boys average 18 push-ups, standard deviation of 4, 34 sit-ups with standard deviation of 11. The mean, their combined totals, therefore, would be 18 plus 34, which is 52. Yeah. What is the standard deviation of their combined scores? Somebody do the calculation real quick. 4 push-ups is the standard deviation, and 11 sit-ups is the other standard deviation. And they want to know the standard deviation of the combined scores. I didn't actually do this calculation ahead of time. You get 11.7. Someone confirm? Okay, several people are nodding yes. Okay, cool, fantastic, wonderful, great. If you marked down 11.7, you'd be wrong. I put this problem up here on purpose. They would throw something like this at you on an AP test, and people would immediately jump into that calculation, and they'd get 11.7. 11.7 is clearly one of the answers. They'd be like, oh, happy day. Mark it off, move on to the next question, and never think about it again. But the problem is, do you think a boy's ability to do push-ups and sit-ups are independent from each other? They're not. See, unfortunately, I shouldn't say unfortunately, but logically, if you are a person who can do a ton of push-ups, logically, you, not most likely, but you could do a lot more sit-ups, and vice versa. If you were someone who couldn't do a lot of push-ups, then probably you can't do a lot of sit-ups. The two variables in question are, it's suspect as to whether or not they're independent of each other. So the answer to this question is actually it cannot be determined. This is something that would mess a ton of people up. And it would. And I even said you would be wrong. And several of you were like, oh, why? For that reason. The two events have to be independent of each other. You have a homework that is already on your Google Classroom. I will be putting out a video probably tomorrow. I have to edit it a little bit, but I'll probably put out a video tomorrow kind of reviewing those questions. And then we'll go from there. We're getting closer. We got about 2.5 weeks until midterms. Anyway, we'll see you then. I'm going to sign off.